Part of the problem we have when we look at exponential functions of the form y equals e to the rt is how do we know that's all of them? For example, we've been looking at exponential functions of the form like b to the t. Let's see here. I'm going to try to get that to match up with the problem on the sheet. If I start out with the exponential function y equals 1.3 to the t, how do I know I can find an r so that e to rt is exactly the same graph? Well, this is how you could do it by sliding. We'll try to do this algebraically in a couple days. But meanwhile, we can see that y equals e to the rt when r equals 1 is growing too fast. I want to slow down how fast that's growing. So I'm going to go over my slider for r, and I'm going to pull it down just a little bit. And you can see that the further I go down, the more the green graph, the one that looks like e to the rt, looks like the graph that we started with. And if I get way over like this, I can almost get it right on top. There we go. That's about, too much. This is funny. Anyways, how about if I do this instead? I'll try to type in a number. Ooh, I think that just about lines up. Yeah, now what do I want here? What do I want to conclude? I want to conclude that the ordinary exponential function that we've been using, 1.3 to the t, is almost exactly the same as e to the 0.26 t. Now, before we go on to the next example, remember that the rate of growth of our original function is 30% because it's 1 plus r minus 1, right? So this graph is going up at a 30% rate. This graph, because it's being compounded continuously, can start with a lower rate, like 0.26, and because it's compounded so much, over a year you'll get the 30%. That is the usual relationship between these two, is that the rate you're going to need if you compound continuously can be less than the rate you're actually going to get over the course of a year. Now let's look at the other example that's on the page. If I take the exponential function 0.8 to the t, I'm going to see this red decaying line, and the idea is, can I find an r so that the red graph of e to the rt exactly lines up with y equals 0.8 to the t? Well, I'm going to try the same thing I did before. The problem is, as long as r is positive, my function is growing. So I want to get r negative as fast as I can. I'm probably going to go too fast. There, it's a little bit negative. Not negative enough. Not negative enough. It's getting there. Getting there. Almost there. Almost there. It's like Star Wars. Almost there. What is it here? Let's see here. If I change this to 2, how's that? 1? Nope, not enough. 3. 4. Ooh, too much. Oh, 2, 5. Ooh, that's about it. Now what do I want here? Yes, I want to start out with an exponential function of 0.8 to the t and find an e to the rt that's exactly the same function. And you can see that the r that seems to work is about negative 0.225, which, by the way, is slightly more negative. This is the same thing what happened before than the 20% decay rate I have here. And that is the usual relationship that's between the two. So that's it. If we start with an exponential function, we should be able to find another exponential function of the form e to the rt where the two functions actually line up. And so anything we say about e to the rt is going to apply to every exponential function in the long run, which is why we're going there.